I love making figures in R. A big part of that is that it's easy to experiment with different ways of visualizing data using the ggplot2 package. Today, I'll show you one of those experiments where I said, I wonder if, and then we'll see that we did it. Hey folks, I'm Pat Schloss, and this is Code Club. Thanks for joining me for another episode. As you know by now, I really geek out about applying principles of reproducible research to questions that I find interesting. Right now, we're looking at a biological question of trying to understand the performance of different methods of analyzing 16S rRNA gene sequences. Those methods are called amplicon sequence variants, or ASVs, and operational taxonomic units, or OTUs. But don't let that jargon scare you away. We could be looking at any types of data. We could be looking at baseball data, stock market data. We could be looking at demographic data. We could be looking at economic data. All sorts of different data would benefit by thinking through things in a reproducible manner. And a big way that we have to do that is by writing R scripts that we can then enter into an overall workflow. And as we've been seeing in recent episodes, using those figures to help buttress the claims that we make in a manuscript, which we are also writing in a reproducible format called R Markdown. All right, so what are we doing today? Well, in the past two episodes, we've made two figures that are going to be the primary figures of the manuscript we're working on. The format I'm working on is an observation format, and MSphere, the journal, for this format allows you two figures. So what I'm going to do is this third figure, I don't think has enough information in it to be a figure in the main body. And so what I'm going to do is I'm going to go ahead and put that into the supplement as a supplemental file. The information that I want people to glean from that are simple numbers that are already embedded in the paragraph. But what I think about when I think about supplemental figures, what I like to think of them as is kind of they're important and people might want to see it, but I personally don't think it adds much, right? So someone else might geek out about seeing these data, but for me, I'm like, I already gave you the actual values. You don't really need the figure. So that's my philosophy. We'll see if the reviewers agree. Let me know if you agree. Tell me what you think in the end of this figure and whether or not it should be a main figure in the paper, or if you think it belongs in the supplement. The figure I'm talking about is a receiver operator characteristic curve. Now let me show you in our GitHub site for this repository for our project. In exploratory, down here I did an exploratory analysis back in December, right before the winter holidays, right before Christmas, where we made rock curves. And so this is a rock curve, receiver operator characteristic curve is 1 minus specificity on the x-axis and sensitivity is on the y-axis. Go back and check out that video right before the winter break if you want to learn more about how we made this. So again, I don't know that there's much to be gleaned from this curve, like the 4 lines for the 4 regions we're looking at of the 16S gene all kind of overlap on each other. They're really smushed way up into the upper left corner of the rock curve space. But what I'd like to do is maybe show this and then annotate where different values sit on the curve. So if you recall from this analysis, one of the things we did was look at the 3% difference, which is normally when people are defining an OTU, they look at a 3% distance between the sequences within the OTU. And so in this analysis, then I put some spheres or some circles on the rock curve to show where the values were, the sensitivity specificity values were for a 3% threshold. I also put this diagonal line to give people context for the line that represented the equal value of sensitivity and specificity. We also looked at what threshold provides the equal balance of sensitivity and specificity. So what values were on that line, that diagonal line I drew. And so as you're perhaps seeing, these circles are showing us the sensitivity and specificity values. They're not showing us the actual thresholds. Those thresholds, again, are in the paragraph in the manuscript. We then also said what threshold provides the sensitivity and specificity closest to perfect classification. And so that's these 4 circles, right? And again, I'm not showing you the threshold. In the figure, the thresholds are in a sentence in the manuscript. So I kind of feel like what I'd like to have is a figure like this, where I have some markings indicating where the values are for the 3% threshold, the equal balance between sensitivity and specificity, as well as the point that's closest to perfect classification. And perfect classification is right here where the finger is on this hand. But if I put all those points onto the lines, it's going to get to be like a really jumbled mess and be pretty just busy, right? So what I think I'd rather have is maybe line segments coming out of the curve to a common point And I can then say, these are the values for a 3% threshold. And then have lines coming out and say, these are the values for the point closest to the upper left corner. And then over here, perhaps line segments, 4 line segments coming in saying, these are the 4 values, sensitivity, specificity values, that correspond to the points closest to the balance between sensitivity and specificity. And again, we can then, in the text where we're actually giving the thresholds, do a shout out to the supplementary figure 1 in this case, where we'll do that. So that's my hope. I don't really know how to do this. And so we're going to figure that out as we go along. Again, that's the power of working with ggplot, is that they make hard things pretty straightforward and easy to do. So I'm not claiming this will be simple, but we'll get to it by the end of this episode. I'm going to come and open up my RStudio project, and I will create a new R script, which I will save into my code directory as plot rock_curve.r. And I am going to then borrow a bunch of code from way up here. Let's see. So we've already got all this great code for calculating the sensitivity and specificity. These values were averaged over 100 iterations, where we grabbed 1 genome from each species in the rRNA database. And let's see, let's get our formatting looking decent here. Run all that, get that loaded. And so if we look at sensitivity, specificity, for each of our 4 regions, we have the distance threshold. So 0 is an amplicon sequence variant, and these other thresholds describe OTUs. We then have sensitivity and specificity for all those different thresholds. Great. Now let's come down, and you'll recall that we had this code to build the plot. So this will be a good seed for the plot we want to build. And so let's make sure we can generate that. And sure enough, there we are. And then we looked at these different thresholds. And so we created one data frame called 3. So I'll insert this up here. And we had one called balance, which again was the points that fall on that diagonal line. And then we had one called distance further down here. That is the point closest to perfect specificity, perfect sensitivity. So I'm going to go ahead and load these 3 data frames. And if I look at 3, I get this data frame, distance, get that, and balance, I get this. And what I'd like to do is to merge these 3 data frames together so that I can use it, that data frame as an argument to ggplot. And so what I'd like to do is there's a function called geom_segment that allows me to draw lines, to draw segments, line segments. And so what I'm thinking is that I could have a line start, say, here, where my cursor is, and then come down to here, right, for 3, right? And so what we might do is to pick, we'll have a line start at, these coordinates and then come to a common point. I'm not doing a good job of explaining it, but we'll get there here in a second. So the first thing I need to do with these 3, distance and balance, is I need to join them together. And so it's not going to be a join like we've done with inner join, but we're going to basically concatenate the 3 data frames together to make a new data frame. And to do that, I need to get them to have a common set of columns. And if you recall, the columns that we have that I'm interested in would be region, sensitivity, specificity. And so I will add a select statement to these 3 data frames. So we'll do select, and we will do region, sensitivity, and specificity. And I'm going to add this to the 3 data frames, and then rerun all those. And now, if I look at distance, I've got the 3 columns, 3 and balance. They're all there. And so we can now join those 3 data frames together using bind rows. And I'll do 3 equals 3, and balance equals balance, and distance equals distance. And I've named these 3 data frames because if I do this, if I run that bind rows command like that, I now have 3 copies of v19, v4, v34, v45 in my data frame, but I really need a column to identify what data frame they came from. And so I can do period ID equals method. And so now I get a column in my data frame for method that gives me the name that I assigned to each of those 3 data frames. Okay. And so that looks great. And I will call this annotation as that. And so that all looks good. Maybe I'll put ID on a separate line so things aren't running off the edge of my screen. And again, we've got annotation loaded in and ready for work. What we'll do then is, if we think about our sensitivity, specificity rock curve, the next thing I want to do is add, or maybe I'll do it back up here. It's not going to be piped. It's going to be added on because it's part of ggplot. We'll do geom segment. I'm going to do data equals annotation. And again, instead of using sensitivity and specificity as the data, for geom segment, then we're going to use the data in annotation. And geom segment has several aesthetics that are required. It requires an X, a Y, an X end, and a Y end. And so we need to then populate these values. So it's X is where the line starts or segment starts, and X end is where it ends. We're not using arrowheads, so I don't really care where things start or end. But what I'm going to do for my X is going to be 1 minus sensitivity from that annotation column, annotation data frame, and then Y will be specificity. And then to experiment with this, for my X end, I'm going to put 0.6 and Y end, or I'm sorry, 0.02 and Y end equals 0.6. So I should have 12 lines that end right about here, right? So there'll be segments that start right where my cursor is and then fan out to the value on the rock curve. So I'll go ahead and add that, see how this runs. And sure enough, there we go. We've got 0.6, 0.2, and then it fans out to the values on the rock curve. And I realize I've flipped, this shouldn't be sensitivity, it should be specificity. So let's try that again. Yeah, so now we've got 12 lines coming to this common point. And what I'd like to have is 3 common points, and each common point representing each method. And again, this is going to take a little bit of fiddling. So before I go too wild with my fiddling, what I'd like to do is output this to ggsave. And I'll put this in figures /rock curve.pdf. And let's do width equals 6, height equals 6. And let's see what this looks like. Where we do open figures, rock curve.pdf. And there we go. Get that to fit in the window. And one thing that is a little annoying about this figure is that all the business is happening way up here, smushed up against the top of the plot. And to highlight the differences between the lines, what I'll do is I'll probably zoom in to, let's say, 0.9, so we can look at the top half of that line. What we can do in the figure legend then is to say what the sensitivity and specificity values were for amplicon sequence variants, which are these endpoints down here. Their performance is much worse than looking at these different distance thresholds. Okay, so to do that, we will come back here, and I'm going to do chord Cartesian, and we will do y lim equals c, and I'm going to do 0.9 to 1. Save that, source it, and see what this looks like. And again, all the points, obviously, that I described are way down, but it allows us to see with greater resolution what's going on here. And again, it's a little bit jerky because it is the product of some randomness. So to improve that appearance a little bit, let's put something at like 0.925. I'm not there, but right there. And make sure that looks good. Yeah. And again, what we can do is I'm going to set different values for x end and y end. And so to do that, we will modify our annotation data frame. To do that, we'll do mutate, and let's do x end. And I will then use a function that I don't think we've talked about before, which is called case when. And it is a function that is like if else, but allows you to have to easily have more than 2 levels. So the first thing we do is ask a question. So case when method equals 3. Then we do a tilde. If it equals 3, where do we want it to go? So I'll say 0.01 for now. Again, we'll likely change this. If method equals balance, I will then put that at, let's say 0.025. And then let's do 2. And then method equals distance. I'll do 0.03 and save that. And then we will then put x end instead of 0.02. I'm going to make that x end. Run that, and whammy. We get 3 different placements for the 3 different methods. I might want to switch my position of balance and distance so that my lines for different methods aren't crossing. So here I'll put 3, and here I'll put 2. Run that, and that looks pretty good. Let me go ahead and put in my diagonal line. I want that to fall behind the points. So I'll do geom AB line with intercept equals 1 and slope equals -1. And I like that color equals gray. And so that looks nice. And we should have some greater separation along the x-axis here. So let's put this at 4, and maybe this at 2.5. And let's look at the PDF version to see what that looks like. So that looks nice. Maybe what I'll do instead is I'll put this balance one up above the line, and then I can move this over a little bit. And to do that, then we need to set the y end. And so we will again do a mutate on y end. And we don't need that comma, but this will be y end. And our 3, I'm going to put at, I guess we have it at 0.925. This one I'll put at 0.975, and this at 0.95. And then I think that should be good. Why is it complaining? This doesn't need to be mutate. We can continue on within the same mutate function call. There we go. And so that's much better. And again, if we look at annotation, we then see that we've got a column for a method, the region, the sensitivity, specificity, the x end, and y end, and we're in good shape. And then we can change this 0.925 to be y end. So let's give that a run, and then our GG save. That looks good. Maybe I'll move the 3 over to the right a little bit, and let's see. So instead of 0.1, let's do 0.15. So that looks good. Good. So this is like what I wanted. So the next thing I want to do is put a piece of text at where these 4 lines all join each other, to then say, these are where the 3% threshold points fell on the ROC curve. This is where the balance fell. This is where the distance fell. Okay. So we can do that with geom text. And again, we'll do data equals annotation, and then AES label equals method. And we will then do x equals x end, y equals y end, and add that into our pipeline. Look at the output in our PDF, and we see that we've got text at that point. So a couple things. The text is purple, which I'm not a fan of. Also, it's putting the text in our legend, which I don't want either. And so there's a alternative to geom text which is geom label. So let's try that, because that will put a box around our labels, right? So we see the box around the label. It's still purple, but we can take care of that by giving it, outside of the AES, we can say color equals black. Let's see what that looks like now. And so now we've got balance distance 3. This is what I had in my mind. So hopefully you think this is attractive. Let's give those labels a little bit more descriptive name. And what I'll do again is another case when. I'll be sure to put a comma after the end of the y end. And I'm going to call this pretty. So it'll be a pretty depiction of the name. So if the method is 3 balance or distance, then I'm going to put, so I'll put 3% distance threshold. Here I'll put equal sensitivity and specificity. And here I'll say closest to optimal classification. All right. And then instead of label equals method, we're going to do label equals pretty. Okay. And we need to be sure to run all this. And we can look at our PDF, and voila, it looks a lot nicer. So these labels are a bit long, and we can insert a line break within the label so that it becomes a 2-line label and looks more attractive. And I'll do that here. I'll do \n is the special character to insert a line break. And again, look at the output here. And that looks pretty nice. I'm pretty happy with how that looks, actually. Good. So a couple things that I still am not totally wild about in this figure. So we need to capitalize the sensitivity and 1 minus specificity. I need to fix the legend to make that look nicer. I'm going to borrow some code from the lumping and splitting plot that we made in the previous episode to do that. All right, so let's do that. So we'll go ahead and do labs, and we'll do x equals 1 minus specificity, and then y equals sensitivity. Check that out. That looks good. And now we need to move our legend. I want to put it down here inside the plotting window. And we also need to fix the colors. And so you'll recall that we can do theme, and we can then say legend position, and we can give it a vector of proportional coordinates within the plotting window. So if we do 0.5, 0.5, we can then see that it puts the legend right smack dab in the middle of the plot, which isn't where we want it. So we want it to be to the right and down a bit. So we'll iterate a little bit to figure that out. So let's do 0.9 and 0.1. And so that puts it maybe a little bit too far down. So that would be, say, 0.2. That looks pretty good. And now I need to tidy up those colors a little. And I'm going to come back to my files where we did plot, lump, split. And you'll recall I had this scale color manual here. What happened? All right, there we go. And I will add this into my my ggplot pipeline here, and I think that should work. Yeah, that looks pretty good. Again, one of the things I didn't like before was that the separation, the vertical separation within the plotting window wasn't ideal. So let's go ahead and maybe tidy that up a little bit. And I think what we saw before with plot lump split was that we had legend key size like that. And let's see how that looks for us. And so that does draw it together a little bit better to show us the 4 lines and the 4 colors. Those colors are not good, and we'll come back and talk about colors in another episode. But for now, that's a good placeholder for us, and I think that looks pretty good. So I'm really happy with how this plot looks. I think it will be a good supplemental figure. The values for where the lines connect, like what threshold is right here at that point, that is in the text of the paper. And so again, I don't think this adds a whole lot except to show the shape of the rock curve and that we really are smushed in the upper left corner of the rock curve. All right, I'm going to go ahead now and add this to my makefile and to my R Markdown document. So let's go ahead and open Atom so we can put that into the makefile. And so we'll make a rule to generate the rock curve plot. And so we can have figures, and we'll call the rock curve dot percent, and we'll do code / plot rock curve dot r. And then that is going to be dependent on data processed / rndb.rock.tsv. And then we will then do period / code plot rock curve.r. And so two things, we need to add the shebang line, and I also need to add the TIFF file. And we'll do compression equals LZW. And this has not been working in the past. I mean, it generates the TIFF, but if we look at the size of the TIFF, it's huge. It's 12 megabytes. It needs to be in the kilobytes because I think the submission system limits you to 3 megabyte files. So if I can't figure this out, then I might have to use another tool. Let me do DPI equals 300 and see if that gives me a different size. Nope, still too big. Yeah, I don't know what's going on with the compression. Sometimes it works and sometimes it doesn't work. So, okay, we've got that working. We also need to add the shebang line here, which I'll steal from my other R script. And we can then come back and we can then make this. Nothing can be done. What? Oh, not for, sorry. We don't want to make the R script, we want to make the figure. Figures, rock curve, .pdf. Nothing can be done for that either, evidently. Let me just check the timestamps on these different things. Let's see. So it should be firing that off. So I must have a problem here. Figures, rock curve, that. Let's go ahead and do cmod on code plot rock curve.r. So for some reason, it's not triggering to build the rock curve.pdf. If I go ahead and put in PDF, it does it. I don't know what its problem is. It should work with that wildcard. I think it worked before. Let me see if let me just touch the code plot rock curve.r and let's try that now. Yeah, so that works. I'm not sure what was going on, why it doesn't like the percent sign, the wildcard. Maybe I'll just copy that for all these as well. Maybe I thought it worked, but it wasn't actually doing what I thought it was doing for these other figures. Anyway, so now we want to make that PDF a dependency of building our Markdown document. We'll go back to that file, submission, where'd you go? Submission, RMD, and then down here, I'm going to go ahead and create a new page, and this will be figure S1, and I will call this rock curve.pdf, and then I'll say receiver operator characteristic curve and position of various thresholds. Okay, very good. And let's go ahead and build that. So we'll do make submission manuscript.pdf. And with any success, we'll have our 3 figures in our manuscript. And I'll open submission manuscript.pdf. And we'll see that's the figure we made in the last episode. And then this is the supplemental figure that we made for this episode. And so that looks great. Again, the colors need a fair amount of help. We'll deal with that next time. And we also need to flesh out these figure captions a bit more. And we also need to then describe the figures or call out the figures in the main body of the manuscript. I think I did put in figure 1 somewhere way up here. Yeah, right here I've got figure 1. But there's other places that we need to put in a call out to figure 2, as well as now our supplemental figure. So we'll do that in the next episode. We're getting there to being done with these figures. I'm really liking how they're working out. Let me know what you think of the figures. I think a lot of this is a matter of personal style. One of the things that I try to do is help my reader interpret the data the way I see the data. Some people say, let the data speak for themselves, but no, really, like, the data can't speak. They're dead. They're data, right? So we really need to help our data to speak and to show the data the way we see it to help advance the description of how we're testing our hypothesis and our observations. Anyway, thanks again for spending so much time with me, watching me go through this analysis. I really hope you've learned a lot and that you're getting value out of this. Please be sure to tell your friends about these episodes. I'd love it if you went ahead and hit that thumbs up button telling me you liked it. That makes me feel good, knowing that you all are watching and that you're liking these videos. Anyway, so long, and we'll see you next time for another episode of Code Club.